Hello, you are all welcome to my class. Today's topic is limits and continuity of functions. Let's begin with basic definition of what limit is all about. By definition, let x naught be an accumulation point of the domain of the function. Then f of x is said to converge to L as x tends to x naught, and we write f of x going to L as x goes to x naught, or you can use another notation as limit as x goes to x naught of f of x equal to L. If for arbitrary epsilon positive, there exists a delta which depends on epsilon positive such that the absolute value of f of x minus the limit point L is less than epsilon whenever the absolute value of x minus x naught is less than delta which depends on epsilon. Now, this definition is what we are basically going to be applying in the proof of limit of functions. And this is what is called the epsilon delta definition of functions. Now let's take some examples. Evaluate the following limits and give a standard argument to justify your result. The limit as x goes to 2 of 2x squared plus 4x minus 16 all over x minus 2. Now how do we handle this kind of problem? You say since the limit is equal to 12, so 12 is our L. For arbitrary epsilon positive, if we choose our delta, we depend on epsilon to be epsilon divided by 2, then the limit is true. However, for arbitrary x in R such that the absolute value of x minus 2 is less than delta, we depend on epsilon, we obtain that this absolute value of 2x squared plus 4x minus 16 all over x minus 2 all minus 12 is equal to, now this expression here is actually from the definition of limits of function, and when you evaluate the absolute value properly, you discover that you are going to have that 2 times the absolute value of x minus 2 is what you're going to have, and that will be less than 2 delta because x minus 2 is delta. Okay, so you have 2 delta less than epsilon, therefore making delta the subject, you now have that delta is less than epsilon over 2. That is how we have epsilon over 2. Delta being less than epsilon over 2 satisfies the limit function. Now, in exam, if you're asked to solve this kind of problem, this is what we expect to see as the answer. Another example, we should evaluate the following limits and give a standard argument to justify our result. Now, the problem is we should find the limit as x goes to 5 of x squared minus 3x plus 1. Solution. Now, when you take that limit, you're going to have 11. So for arbitrary epsilon, we may consider that delta, we depend on epsilon, should lie between 0 and 1 from experience. Now, when we take the absolute value from our definition of functions, limit function, this is what you're going to have. And at the end, you're going to have that delta will multiply absolute value of x plus 2. And knowing that our absolute value of x minus 5 is less than delta, that is how we got that delta there after the expansion. And by the time you do a proper evaluation of the delta, you're going to have that 8 delta will be less than epsilon. Now, if this delta, provided that delta E is less than 1, now making delta the subject, you're going to have that delta will be less than epsilon over 8. Now, the relationship there will now be that delta, we depend on epsilon, will be less than the minimum of 1 and epsilon over 8. We have that 1 there because we assumed delta to be less than 1. Now, the next topic is infinite, or subtopic is infinite limits of function. Now, by definition, we're actually looking at those functions whose limits tends to infinity. That is what we mean by infinite limit of functions. Now, let's take some examples. Prove that the limit as n goes to infinity of 3n plus 1 all over 7n minus 45 is equal to 3 over 7. We should prove that this limit as n goes to infinity will give us 3 over 7. Solution, how are you going to prove that? You say for each epsilon positive, we need an n which depend on epsilon, and they must be a member of the natural number such that this absolute value 3n plus 1 over 7n minus 45 minus 3 over 7 will be less than epsilon for all n strictly greater than n which depends on epsilon. So we estimate as follows. When we take the absolute value again of f of x and L, you're going to have the expression on the screen, and when you evaluate properly, you're going to have that the left hand side will now be equal to 284 over 4n. Meanwhile, we have gotten our initial n to be n strictly greater than 90 over 7. Now we are going to look for the second n, and that is what we are looking at right now. So 284 over 49n is less than epsilon. Now make n the subject. When you do that, n will now be strictly greater than 284 over 49 epsilon. But we already know that n is greater than 90 over 7. Therefore, our final result, or the final n which depend on epsilon, should now be the maximum of 90 over 7 and 284 over 49a. Let's look at more examples to deepen our understanding. Now, we should prove that the limit as n goes to infinity of all n raised to power 3 plus 3n all over n cubed minus 6 is equal to 4. Solution. For each epsilon positive, we need an n which depend on epsilon such that the absolute value of f of x minus L will be less than epsilon. This is from definition. So when we estimate, we'll break it down into this. And if you follow the steps religiously by factoring, you're going to have 54 over n squared, provided n raised to power 3 over 2 is greater than 6. Now, when you continue with the evaluation and making n the subject, you're going to have that n will be greater than square root of 54 over epsilon. But we already know that n cubed over 2 is greater than 6. Therefore, to get n there also, you're going to have that n will be strictly greater than 12 raised to power 1 over 3. So we choose our n, we depend on epsilon, to be the maximum between 12 raised to power 1 over 3 and square root of 54 over epsilon. Now, the notation you're seeing there is a greatest integer function. Now let's move on to continuity of functions. It's closely related to limit of functions. Now, by definition, a function is said to be continuous at a point if f of x minus f of x naught is less than epsilon, whenever the absolute value of x minus x naught is less than delta. Let's use that definition to implement and see what we have. Let's look at this example. Should prove that f defined by f of x equal to 3x squared minus 2x plus 1 is continuous at x equal to 5. We should prove that. Now, let epsilon be given. We want to find the delta such that if the absolute value of x minus 5 is less than delta, then f of x minus f of 5 will be less than epsilon. Now, when you do the evaluation and substitute properly, you're going to have that f of x minus f of 5 will be equal to 3 absolute value of x plus 5 plus 2, all multiplying delta. And when you evaluate further to find the value for 3 multiplying x plus 5 plus 2, you're going to have 35. Now you continue with the evaluation. You're going to have that delta is equal to epsilon over 35. Now recall that we choose our delta to be less than 1. So given any epsilon, we choose our delta to be the minimum of 1 and the epsilon over 35. Then f of x minus f5 will be less than epsilon whenever the absolute value of x minus 5 is less than delta. And that satisfies our condition for continuity so that f is continuous at 5. Let's pick another example. Say prove that the function f defined by f of x equal to 3 plus 2x cubed is continuous at x equal to minus 4. The proof is simple. You're going to evaluate f of x minus f of L, the point of continuity, and that will give us, when you evaluate properly, you're going to have 2 times, you're going to be here 2 times absolute value of x cubed plus 4 raised to power 3. And when you do your proper evaluation, you're going to have that 2 multiply x squared minus 4x plus 4 raised to power 2 times delta. So, but that is, we already know that the absolute value of x plus 4 is less than delta. Therefore, that will imply that this expansion is going to give us 122. Hence, 122 delta is equal to epsilon. And when you make delta the subject, you're going to have epsilon over 122. Therefore, the delta we are going to choose, which will satisfy the condition of continuity at this point, is the minimum between 1 and epsilon over 122. So, this is how to show it. Thank you for listening. Bye.